Continuing on the theme of environmental monitoring, I'll now introduce you to a Barebones circuit that can log data to an Internet of Things website known as Thingspeak using cellular networks. In future videos, I'll explain how to add a simple environmental sensor like this water sensor, solar panel and battery charger, and an enclosure to help you transmit environmental data to the Internet from a location away from power and exposed to the elements. But for now, let's just focus on this simple circuit. Let's get started. For this circuit, we'll be working with the Adafruit FONA, which is essentially an Arduino compatible cell phone. I'll just refer to this hardware as the FONA from this point forward. Now, I realize the FONA doesn't exactly look like the Arduino Uno we've been experimenting with, but don't worry, for the purposes of this demonstration, the only real difference is the form factor and the fact that a cell phone is embedded on the circuit board, which really simplifies things as it relates to wiring. In addition, this hardware runs nicely on 3.7 volt lithium batteries, which makes it ideal for field deployments. It's also well supported in the Arduino software, meaning it can run just about every sensor library you might be interested in, and it also has the same options as the Arduino Uno for stacking different technologies like data loggers and OLED displays. Please note that there are hardware alternatives to the FONA, many of which you can find on eBay at much lower cost, but the difference comes back to Adafruit offering excellent documentation and comprehensive software libraries that really help non-electrical engineers like me. The FONA does require installation of a library and driver on your computer in addition to some minor soldering. Having said that, Adafruit has prepared an excellent guide on this hardware that you can reference for the same. So I won't repeat the steps here outside of providing the link in the description of this video. For this demonstration, please review that documentation. The FONA comes with standard headers, but I recommend picking up these stacking headers since it opens up possibilities for adding hardware on your FONA or easily plugging in jumpers for sensors during testing. In my demonstration, I'm using the feather stacking headers. We'll also need a GSM cellular antenna with a UFL connector. Also, I'd recommend this LCD shield kit. The LCD shield is not necessary for running our code, but does give us the ability to see how the code is performing when the FONA is not attached to a computer, say when we're deployed in the field or for debugging. A link for the libraries needed to use this shield are included in the description of this video, and I do use the shield in my demonstration. Since cellular connections can draw more power than our USB port can provide, you can use a LiPo or lithium-ion battery with a JST connector. In my demonstrations, I'm using a large 4400 mAh lithium-ion battery, which I just happen to have in stock, but you can just as easily use any of the lower capacity LiPos sold by Adafruit. For this first demonstration, all these components will be attached to a breadboard and connected to one another via a suite of jumper wires. Also, in order to upload our programs, also known as sketches, to the FONA, we will need a USB A micro cable that we'll use to attach the FONA to our computer's USB port. And since we'll be using cellular service for posting data to the Internet of Things, we'll also need a registered SIM card. I've had pretty good luck with TING, which is a T-Mobile reseller recommended by Adafruit that works flawlessly with their hardware. If you go with another carrier, please note you'll need to make sure that the carrier offers 2G service, which is what the FONA recognizes. For working with the Internet of Things, 2G offers plenty of bandwidth. Assuming you don't have any of these components in stock, this is what you might expect to pay if you purchase from Adafruit. Now, that's not bad for a hardware that can post environmental data to the Internet of Things from anywhere you have 2G coverage. As an alternative, I've looked at formal prepackaged commercial options, and these can run into the thousands of dollars, not including cellular service contracts. So building your own is a nice alternative if you have the patience to figure things out. Once you have all your hardware, the first thing you'll need to do is set up the necessary accounts. Assuming you purchased your SIM from TING, you will need to create an account on the TING website and associate the CCID number printed on your SIM with the credit card for billing. First, you'll create an account. Then select the option, I have a TING GSM SIM card. Then go ahead and enter the CCID number printed on your card, and don't worry about the heads up on the screenshot. The FONA Feather works fine with this SIM. After you've entered this number, just provide your billing information and you're all set. Now that we have a registered SIM card, we can install it in the back of the FONA. Next, let's wire up our circuit onto our breadboard as shown. This wiring will work with the code I will be sharing and demonstrating. And this is what our setup should look like after everything is said and done. Now your wiring may differ slightly. You don't have to exactly match what I've shown here, as long as the right pins are talking to one another. Also notice that since I don't have a switch in this circuit, the battery is unplugged when the circuit is not in use. Next, we'll need to select an Internet of Things platform to receive data that we'll be communicating from our hardware. Please note that there are lots of Internet of Things platforms out there for your consideration, but I've found Thingspeak to be very user-friendly and robust, while offering support for some interesting applications like ThingsTweet and MATLAB Analytics. So for the purpose of this demonstration, I'll be using the same. With respect to cost, Thingspeak offers free accounts for non-commercial use, which also allow you to post over 3 million messages per year to multiple channels. If you're affiliated with a commercial or government agency, eventually you'll want a standard license if or when you've determined that Thingspeak is the right platform for you. Once you're logged in, click on the Channels tab. That will show you all the channels registered to your login and give you the opportunity to create a new one. For the purpose of this demonstration, let's create a new one. Upon doing so, we'll need to give our channel a name and a description. We also need to collect a minimum of one field value. For this demonstration, let's call it Demo, and let's name our field 1 millivolts. Scroll down to the bottom of the screen to save your changes. And upon doing so, you should see a graph that will host the data that's going to be posted to your channel. At this time, we don't have any data, so the graph is empty. Next, click on the API Keys tab. Here you'll want to record the right API key, which we will need to embed in our code later on so that our cellular connection posts our field data to the correct channel. The format for posting data to Thingspeak is shown right here, so this is what you'll want to mimic in your code. Great, so up to this point you should have a FONA with an activated TING SIM card and an LCD display wired to a breadboard, your Arduino integrated development environment installed and configured with the appropriate drivers and libraries necessary for working with our FONA and/or LCD display, and you should also have an account on Thingspeak with a channel and a write API key for writing data to the Internet of Things. So let's go through the Arduino sketch that supports the demonstration I'll be showing you shortly. A link to the sketch is included in the description of this video for your use and modification. I won't go through every line of code, but will highlight some important variables and functions that will help you understand and modify this for your own purposes moving forward. If you're not interested in programming or just want to move forward to the demo, feel free to skip this section. Before we enter our setup loop, we'll include our FONA.h and LCD shield libraries so that we can call up associated functions. Then we'll create an object of type Adafruit RGB LCD shield called LCD that gives us access to the associated library functions for working with our LCD. Take note of these three global variables: my channel, my URL, and my bat. All three of these are important for building a string that will allow us to post data to our Thingspeak channel, as you'll see shortly. Here are some pin definitions that will be fixed throughout our sketch for communicating and controlling our cell phone. The first four are already predefined in our hardware and should not be changed. The fifth here, identified as FONA key, is the pin that we'll be using for toggling the power of our FONA on or off for power savings. We'll also create a software serial object called FONA SS that will facilitate communication between our microcontroller and the cell phone on the board. And we'll create a FONA object that gives us access to the functions associated with the Adafruit FONA library. Finally, we'll create some variables for storing the cellular connection and power status of our FONA. Based on the status of our connection, we can enable or disable functions in the main body of our loop through the use of conditional statements. Next, let's get into our setup block. Here, we will give our user the heads up that our code is executing through a friendly Hello World statement. As a side note, I'll use these large blue arrows to show where text is being echoed to our LCD, and then also include a snapshot of the LCD during code execution. In this block, we're also going to define the string for the channel that will be updated in Thingspeak. Here, I've hidden the channel I'm using in this demonstration in red to avoid confusing posts to my channel from my fellow YouTubers or colleagues at work. You'll have to add your own channel key here for your own setup. Please note that the demo key you see here on the screen is for a channel that no longer exists. After exiting setup, my sketch will start its loop function. This is the block of code that repeats itself until I reset or power off my hardware. Here, let's echo back to the user that we're starting our loop and reset our connection status variables so that nothing is carried over from our last loop iteration. Next, we're going to call a function to turn our FONA on. And here's that function. First, we'll echo back that we're in the function and checking in on the FONA. And then we'll try to communicate with our FONA. If our last iteration of the loop completed successfully, the FONA should currently be off for power savings. As such, we echo the condition back as no FONA and call this key toggle function. The key toggle will execute an electronic switch for turning our FONA on or off depending on what state it's in. If the FONA is off, this function will turn it on. We then echo what we're doing back to the LCD and briefly ground the key pin on the FONA via pin 10 as shown in the lower left of the screen. Again, this will have the effect of turning the cell phone on when it's off. When the FONA gets turned on from an off state, you will see a small blue LED start to blink rapidly. So I'm just going to take a quick detour here and mention something very important about this hardware. If you want to be able to use that toggle function, you need to make sure that you cut the trace on this keypad, which I have circled in red, and this little pad's going to be on the bottom of your FONA. If you don't cut this trace, that toggle function will not work. So just a heads up, and I hope this saves you some time. Once the FONA is registered on the network, that fast blinking LED will slow down as a visual cue that the cell phone is registered on the network. It can take a few seconds for this to happen, but our function will continue proceeding regardless. We then echo back to the screen that the function is done, delay for 2 seconds so that we can see the message on the LCD, and head back to our FONA on function. If our FONA is still having trouble after the key toggle, the code will echo still no FONA to our LCD. This will keep the sStatus variable set to 0 as defined at the top of our loop function, which will result in most of the remaining functions in the loop block being ignored until we try again in a few minutes. In our demonstration, our FONA will turn on and we'll see confirmation on the screen telling us that the FONA is now on. We then set sStatus to 1 here. If for some reason the FONA was already on at the top of the loop, we simply echo FONA found and set sStatus to 1 here and then move on. If sStatus is equal to 1, as you'll see shortly, the conditionals for most of the remaining functions will be true and we'll be able to execute those functions. Next, we'll read our battery voltage using this function. And now we're in that function that reads the battery voltage and then echoes the results to our LCD. Next, I let the FONA sit for 15 seconds. The reason I do this is I'm usually working in areas with poor cell phone coverage, so although my FONA may turn on successfully, it doesn't always get registered on a network immediately. By giving the FONA some time, I increase the chances of it registering properly before moving on to the next step. Now, I realize I could set up a while one loop here, which would have the program wait until the cell phone is properly registered, but I prefer not to do this since it can sometimes take quite a while to get registered in the areas that I'm working with. And this in turn could drain my batteries. Now, if things don't work out in the first 15 seconds, my code will cycle the attempt a few more times and eventually drop the effort if no connection is made. This saves my batteries in situations where I'm concerned about power and allows me to try again in a few minutes based on my loop delay settings. Your needs may vary. After the 15-second delay, my code calls this function to test the registration. Within the FONA reg function, I'll call this netStat function, which checks the registration status of my cell phone. In netStat, I'll check my registration status and return that value to my endStatus variable based on values already defined in Adafruit's FONA library. I'll then echo the status to my LCD screen based on which one of these conditions is true. In my demonstration, my phone successfully registers on the network. That sets the end status to 1, which is important for unlocking other functions in my main loop. I'll then echo that status as registered home since the associated condition is true. Back in my FONA reg function, since endstat is equal to 1, this conditional will allow me to return to the main loop via this break statement. Okay, so now I'm back in my main loop block. At this time, my cell phone is on and registered. Now, since end status is set to 1, this conditional will let me attempt to put the cell phone in GPRS mode, which is the data mode that will be used to post information to the web. So here I'm echoing that we're going to call my GPRS function in 3 seconds, and here we go. The GPRS on function is now called. Okay, so now I'm in the GPRS on function. Let's echo to the screen that we're entering GPRS mode and call a function to do just that. If the phone managed to get into GPRS mode successfully, I'll echo that to the screen and set my gStatus variable to 1. In my demonstration, this will be the case. This function then returns me back to the main loop. Okay, so back in my main loop, I check the status of my cell phone by referencing that gStatus variable. If it's 1, then I can proceed in attempting to post some data to the Internet of Things. First, I need to store the numeric value vbat into a string variable, which I'll call mybat. This allows me to append the respective value to my URL string, which needs to follow the format set by Thingspeak for posting data to its server. In the case of my demonstration, the connection is good, so I echo that I will attempt a data post in 3 seconds, and then call the GPRS post function to do the same. And now I'm in that function. I give the FONA a few more seconds to let the user know that I'm about to post some data. In my field tests in areas with poor coverage, I've found that once my GPRS mode is on, including a delay here helps GPRS register correctly and fully, thus avoiding drop data posts to the Internet of Things. Next, I echo that I'm posting. I then have to get the string associated with my URL into a character array called URL. Character array is the data type recognized by the function that will send the string to Thingspeak. I then attempt to send the character array called URL to Thingspeak and use a conditional to determine whether I was successful. In the case of my demonstration, the transmission is good, so I end the post function appropriately. And return to my loop. Here, I echo that I'll attempt to shut down GPRS mode in 3 seconds, and then call a function that helps me do the same. Now that I'm in my GPRS off function, I again use a conditional to determine if exiting the GPRS mode was good. In the case of my demonstration, I echo that all is well. So now I'm back in my main loop block. And although I'm out of GPRS mode, my cell phone is still on, so it's time to shut that down for power savings until my next data read. Here I echo that I'm shutting down the FONA and call a function to do the same. Once I'm in the FONA off loop, I close my serial connection to the FONA hardware. This must be done before I power off the FONA, or it will cause problems when I try booting the FONA again upon my next loop iteration. I then echo what I'm about to do and again call the key toggle function that I demonstrated earlier. And finally, I'm at the bottom of my loop block where I set a delay to pause for 2 minutes until my next reading and echo the same to my LCD screen, specifically that I'm in a pause state for power savings. Okay, and here's my circuit ready to be tested. Hello world means I just ran through setup and now I'm in my loop function. I'm going to be checking the FONA to see if it's on. Should be off if everything shut down correctly from my last iteration. And this does take a few seconds. No FONA was detected, so now I'm going to toggle that key pin. And you can see that that caused that little blue light, that LED indicator, to turn on. And you can see it's blinking relatively fast. So now my FONA is on, and the sketch recognizes the same. I'm reading my battery voltage. I'm going to wait 15 seconds for the FONA to get registered on the network. And I'll know that because that blinking light will start to slow down. You can see that now it's not pulsing quite as quickly, which means that it's registered, confirmed on the screen. Now I'm going to go into GPRS mode. I'm entering my GPRS mode, and watch the blue light. What happens? See how it's gone a little bit quicker? That means that I'm currently in GPRS mode. I'm waiting 5 seconds before I post. Posting, let's take a look at the Thingspeak screen. And let's wait a few seconds for that post to take place. And I've already got one data point on there to make it easier to see the next data point when it posts. And there it is. Let's come back down. The loop is done, and now I've paused for 2 minutes in this case. Now, there are many things you can do to customize this code for your own needs. For instance, you could modify the time delay to save on data costs if you don't need conditions forwarded every 2 minutes. Or you could make the measurement happen in response to some change in environmental condition by using what are known as interrupt pins. You could also eliminate all the echoes and delays associated with the LCD, since these are primarily for debugging, and you don't really need an LCD attached to your circuit when it's running in the field. Or as an alternative, maybe you can keep 1 or 2 in your code just to check on things when you visit your installation. You can bring an LCD along with a homemade cable and just plug it into a wired port to check in on the same. As a Barebones sketch, note that this program only registers battery voltage to our Internet of Things website. Now, that's not very helpful on its own, so you'll definitely want to incorporate some additional variables and functions for registering other environmental conditions like temperature, humidity, presence or absence of flow or rain, or anything else you may be interested in. This is a good place in the code for calling those functions, which you will need to write on your own, and then create variables for storing and posting that data accordingly. In doing so, you'll want to make sure that you've set up Thingspeak with additional fields to receive that data, and update the myURL string to report out that data to the Internet of Things. So before you invest money and time in this Barebones system, you might wonder if it's been tested for more than a couple of data posts. Well, my original design was mounted on a breadboard and housed in a kayaker's lunchbox, used more expensive hardware components, and employed an older sketch that was difficult to read and had a few bugs. For all its shortcomings, it still held up very well to the elements and worked flawlessly for 9 months with no maintenance. The new design reflected in this video uses more modular hardware that is easier to configure and wire, is housed in a box that's approved for outdoor electrical applications, and is running an improved sketch that is easier to read and amend. For the conclusion of this video, let's summarize field testing of this new design to ensure nothing was broken in my upgrades. I know this doesn't look like our breadboard circuit, but I assure you the circuit is exactly the same as what was presented in this video and is running the same code. I'll explain what all the added hardware components are in a future video. Suffice it to say that they're for solar power and to facilitate adding sensors. So let's see how she does. So this slide shows the battery voltage posted to Thingspeak the evening and morning before I exited for a camping trip. You can see here that the system is reporting fairly consistently for a site that has very poor cell phone coverage, and that the voltage profile is acting as I would expect it to, decreasing overnight and then increasing thanks to my solar panel charging things up in the morning. Okay, so here's my setup out here in the Tucson Mountains in my backyard. Cell phone reception out here is pretty bad, which is actually good for my purposes because I suspect that some of the places where we will be installing these remote environmental monitors have pretty poor cell phone reception as well. So I won't be surprised to see a little bit of drop data. I'm going to let this run for the next couple days while I'm camping out at Organ Pipe. And when I come back, hopefully we'll have some interesting metrics to report. It's a little after 5 on a Saturday, after 2 lovely nights of camping at Organ Pipe. Just coming back to check out how this thing is doing. Let's open it up. So that's what it looks like on the inside right now. That little red light on the solar LiPo charger means that there's power from the sun going to the charger, and the green light means that that LiPo battery is charged. So that's working pretty good. And here's my Thingspeak screenshot. You can see that I have my channel set up, and here is the data that's recently been registered up to now. The channel was created 5 days ago, but it was updated 2 minutes ago. It's actually only been recording for the last 3 days or so. I've got 624 entries, and if I want to see the full record, I can click on this little pencil right here, and I can enter 624 there to show all 624 entries. And you can see that there's my my battery charge discharge profile. So what's happening is it's discharging during the course of the day and overnight, and in the morning with the morning sun it charges up again, and then it discharges, and then charges, discharges. So looks pretty good. This is kind of what I expected to see. I don't see a lot of data gaps in here. Let's change the results back to 60. And you can see that the data that's being collected is pretty consistent. So I don't see a lot of a gap suggesting that that my telemetry is poor, that it's dropping data along the way. So this looks pretty encouraging for the code that's been redeveloped for this remote environmental monitor. This slide shows all the data collected by Thingspeak during the entire period I tested this circuit, a period of about 1 week. Let's zoom in on that profile. This highlighted section shows the REM reporting the evening and morning before I exited for my camping trip. And this shows the data reported during my trip. And this is the data reported after I returned from my trip. This reflects my decision to leave the circuit running for a few more days just to make sure the hardware and programming was robust. If you'd like to review the raw data in spreadsheet format, I've included a link in the description of this video. I should clarify that I'm trained as a hydrologist, not a programmer, so please consider my code for what it is. Really, it's a bare-bones framework to help you get started, prepared by someone who's enthusiastic about the Arduino platform, but really not formally trained in programming. As a hydrologist, my next video will explain how to add a function to this sketch for posting flow and stage, measured in an ephemeral wash, to the Internet of Things. In the interim, you're welcome to take this code, modify it, and redistribute it for your own purposes. But please do acknowledge Adafruit and yours truly if you do so. If you've enjoyed this video, please consider giving me a thumbs up. Subscribe for updates, and see you next time.